Good afternoon. I would like to start my talk. For the next hour, I plan to entertain you on the topic of high entropy alloy catalysts, which is currently a trending topic in literature, which resulted in a exponential growth in publications mentioning high entropy alloy catalysts, and also the number of citations that are citing papers topic with high entropy alloy catalysts is growing exponentially. So what are high entropy alloys? The field of high entropy alloys dates back to 2004, when two researchers, Brian Cantor and Jinwei Yi, decided to see what happens if you mix 5 and more elements together. And back then it was a very brave endeavor, because if you take 5 different elements and you mix them together, you can imagine that you can create a lot of different material structures. And if you, as a result, get a soup of different material structures, you cannot deconvolute it anymore. So people were discouraged to do it until this work. And to everyone's surprise, both works show that if you mix so many different elements, you get a single phase material. And that gave birth to the field of high entropy alloys. And since then, they were studied mostly for their mechanical and thermal properties. Also, in that period, the definition of high entropy alloys was created. And Jinwei Yi defined high entropy alloys as alloys that have a mixing entropy larger than 1.5 R. And this mixing entropy is sufficiently large to rival the entropy of formation of intermetallics, and that's why they break down and create a single-phase, highly disordered structure. Commonly, this definition is also reworded as an alloy that is composed of at least 5 different elements, because that's the minimum criterion to get a mixing entropy larger than 1.5 R. So around 15 years later, Jan Rosmeisel decided to look into high entropy alloys for electrocatalysis. And they published this paper in Joule, which investigated high entropy alloys from a theoretical perspective. So in this work, the researchers used the descriptor-based approach. And to understand the descriptor-based approach, we quickly need to go into the basics of heterogeneous alloy catalysis. So if you have a heterogeneous catalyst, it is supposed to bind catalytic intermediates to its surface. And the strength of this binding should follow the Sabatier principle. It shouldn't bind the intermediates too strong, because then the catalysts are getting poisoned and will not continue further. And also it shouldn't bind the intermediates too weak, because then they will not activate their bonds and the catalysis will not take place. So the perfect catalyst will bind an intermediate just right. So if you now have pure metal catalysts, the binding energies of the intermediates will depend on the catalyst material. And the only way to change the catalytic mechanism and the activity is to change the entire material. But if you now create an alloy, you create new active sites, which are a mixture of multiple elements. And these will have a slightly shifted binding energy towards the reaction intermediates. And according to their work, if you create a high entropy alloy and you have a variety of different elements at the surface, the binding energies become a continuous function. So you can very precisely tune the binding energies of intermediates on your catalytic surface. And because you can very precisely tune them, it becomes possible to design active sites which have the optimal binding energy and will most efficiently catalyze a reaction. So this suggests that in the field of high entropy alloy catalysis, we can find novel catalysts that can rival the current industrial standards. So based on this paper, Jan got his funding for the Center for High Entropy Alloy Catalysis. And this opened in 2020, and this is also where I started my PhD to investigate high entropy alloys. And the first task that I received in my PhD was to find a project to do within the field of high entropy alloy catalysis. So typically, if you want to design an electrocatalytic study, there is a ready template. And if you now would look on Google Scholar and check which publications were published today, you will find multiple publications following this exact template. You create a material. After that, you characterize the material with many characterization methods to give a good image of it. You measure its catalytic performance and you have a ready publication. But if you are looking into the field of high entropy alloy catalysis, you need to make a decision. Which material are you going to study? And here we face the challenge that the field of high entropy alloys has a wide variety of different compositions to choose from. So now let's say we have a selection of 20 different elements, and we try to make a 5-element alloy out of them. We can already make more than 10,000 possible combinations. In addition, we can start to tune these compositions. And if we tune them by 1 atomic percent, Within a single 5-element combination, we can make 4 million possible compositions. So right now we're already talking about something which is 4 times 10 to the power of 10 possible compositions. I hope all of you know that the periodic system is more than 20 elements. And also we don't necessarily need to limit us to 5-element systems. And if you look into literature, you can find also publications that synthesize a 16-element alloy. So Brian Cantor himself estimates that the total number of high entropy alloys would be something like 10 to the power of 78. And this number is larger than the number of atoms in the universe. To make matters worse, we also have no knowledge about the catalytic mechanisms of high entropy alloys. So how do we make now our decision? And I think the way of choosing a high entropy alloys is facing the same problem as the burdens as paradox. Are you familiar with this paradox? So if you take a very hungry donkey and you put him exactly between 2 equal stacks of hay, the donkey is going to starve. And the only way to save the donkey is to perturb the system and give him a nudge in one of the directions. Similar to high entropy alloys, we have an abundance of choices and we have no rationale to make a choice. So we need to find a way to perturb a system. And the way that I found to perturb a system, I got from the paper of Nugraha and co-workers, where the researchers used Bayesian optimization to optimize the platinum palladium gold film towards methanol oxidation. And then I decided, why should we not use the same methodology within our high entropy alloy research field? So now we have a mathematical framework and we want to use it in our laboratory experiments. So the first thing we need to do is we need to transform our everyday experiments into a mathematical framework. And while it may sound scary, it's something that we actually do very often. We think of our experiment as a black box function of which we don't know anything. We have our handles, our input parameters that we can vary. By varying our inputs, we look at the response of this black box function. And typically we limit our study by fixing all possible input parameters and vary one at a time. This way we get a small puzzle piece of our black box function piece at a time. So now as we have transformed our experiments into a mathematical black box, we can also apply all mathematical operations to it. So now let's use Bayesian optimization to optimize a high entropy alloy composition. So as our target is now the composition, this is going to be the input that we are varying. So we start off by choosing a random set of compositions for which we evaluate the activity. So now we have a data set of compositions and activities, and these we can use to train a Gaussian process. And the interesting thing about the Gaussian process is that it is a model that not only predicts an unseen activity, but it also gives a certainty to the associated prediction. So we end up with a probabilistic model, which we can search for compositions that have a high probability of being a novel maximum. After we identify such a composition, we need to evaluate it. And once we evaluate it, we have a slightly larger data set. And we can continue the cycle until we reach a termination criteria. This termination criteria is something that you have to choose yourself, because on one hand, you don't want to try out all possible combinations, because if you try everything, then why do you use an optimization algorithm at all? So the termination criteria can be a target that you need to reach for your industrial application. So a minimum activity that you need to get your product on the market. But it can also be a convergence criteria. So let's say if within 10 cycles you don't see anything better, you can also terminate. And of course, we can be constrained by our resources. We can have funding to perform 150 experiments. And once we have done 150 experiments, no matter what, we have to stop because we are out of time or out of resources. Now I presented this concept in the Center for High Entropy Alloy Catalysis, and it was very well received. And my colleague, Dr. Jack Patterson, decided to investigate the use of Bayesian optimization for high entropy alloy catalysis using a theoretical framework. So he constructed 2 DFT models. And the nice thing is that once you have a DFT model constructed, you can very quickly do predictions. So you can use a grid search to evaluate where the optima are located, so you know your reference point. So when the optimization algorithm has found the global optimum. Also, making a prediction using a constructed DFT model is relatively quick. It takes several seconds. So you can perform the optimization algorithm multiple times and thereby benchmark how strongly a random parameter that we have in the algorithm is affecting the reproducibility. So eventually he performed 64 optimizations on each of the 2 spaces, and each lasted for 150 iterations, and that was sufficient to identify the global optima. So moving on to the results, the first space is the iridium, platinum, palladium, rhodium, ruthenium space, which has two local optima, with similar activities. And on average, it takes 20 iterations to find both of these optima. So if you need just 20 experiments to find the optimal compositions among 4 million possibilities, that's relatively fast. It's also a number we can do in the lab. In case of the silver, iridium, platinum, palladium, ruthenium space, it takes a bit more iterations to find the global optimum. The reason now has to do with the fact that there are 4 optima present. And sometimes the algorithm finds a local optimum and spends some time trying to improve this local optimum before moving on to a next unexplored region. So here on average, you need 50 experiments. And this 50 experiments became more or less a standard in the field of high entropy alloy catalysis as an average number of experiments you need to do to search for an optimal catalyst in the high entropy alloy space. The other thing that this work allowed us to do is to evaluate how well data sampled from Bayesian optimization can be used for machine learning applications. And for this, we can construct so-called learning curves. So the way we construct this is we take the data set as sampled by the Bayesian optimization, we fit a Gaussian process, and then we use this Gaussian process to predict the values of a known grid. And the difference between the prediction and the true values of the grid gives us an insight on how well the Gaussian process can reproduce the underlying DFT model. So what we see is that the mean absolute error of this prediction is decaying exponentially. And around 50 experiments, we observe our first plateau, and it further nicks down at around 80, 90 experiments to I would say, a space that is more or less the same to the DFT space that has been calculated. We can also visualize it using these ternary plots. And you can see that going from 15 experiments to 50 experiments, we have drastic changes in our contours. But the moment we go from 50 to 150 experiments, there are only minor changes. So we are just fine-tuning the space instead of observing new large changes in it. So while Jack was benchmarking it computationally, I was evaluating the use of Bayesian optimization in the lab. And in this work, I was optimizing the platinum, ruthenium, palladium, rhodium, gold composition towards the CO oxidation reaction. And as I'm now working in the lab, I cannot rely on just computational studies, and I have to find a way to get these materials. So I use a synthesis method that was discovered by Jonathan Quinson, and he saw that if you take several chloride precursors in alkaline methanol, and you add gold chloride to it, it initiates a reaction, and within a couple minutes you have nanoparticles. So this is a very easy method to use, and I used it during this work. And then the nanoparticles I had to evaluate for the CO oxidation. So the way this CO oxidation potential was measured is I started off by poisoning the surface with CO, which results in the dying out of the activity, as you can see over here. After that, the CO is substituted with hydrogen, and then it is being stripped by a positive sweep of the potential. So the moment CO is being oxidized on the potential, you produce active sites that can perform the hydrogen oxidation reaction. So the hydrogen oxidation reaction acts as an amplifier of the moment that the CO is leaving the surface, which results in this very sharp spike in activity. So after doing a background correction, I defined this small point as the onset potential. So we want to find catalyst that has a very low potential at this current. So now we can summarize this optimization into the following loop. So right now, as I am trying to optimize something that I can control, I decided to optimize the precursor ratios in the synthesis process. Because the precursor ratios I can control, whereas the composition that I'm getting out of it is a consequence of the synthesis. So strictly speaking, I was optimizing the synthesis to produce the most active catalyst. The results are then shown over here. Also, because I'm now working in the lab, I am often limited by weighting processes that are beyond my control. If I have to dry a sample, I have to dry it for a day, and I cannot accelerate it by using a fan. So the Bayesian optimization was used to suggest batches of experiments so they can be executed in parallel. And we see that in the first cycle, so in the first batch, we already find the global optimum, which has a precursor mixture predominantly composed of platinum, ruthenium, and rhodium. In subsequent cycles, we see that the optimization algorithm is suggesting samples rich of ruthenium. And thereby we see that the CO onset potential is more or less stable and is the most active. In the last cycle, we decided to manually add samples which have a low amount of ruthenium to verify whether we have converged or there are some unexplored regions. And as these samples yield samples which have a high onset potential, we decided that we converge and we indeed found our global optimum. So now we are left with a data set of different nanoparticles and different associated activities. And these ones we can now use to train a random forest regression. And this is now a multidimensional model, so we cannot nicely visualize it. But we can use shapely additive explanations to look into the correlations and the way the random forest is making its decisions. And this is the figure you can see over here. The way to read this figure is to look at the spread of the shop values. So the larger the spread, the more important is this feature to the prediction. And then using the color scheme, we can see how this feature influences the prediction. So for this specific experiments, we see that ruthenium is the key element that drives the prediction of the model. And large amounts of ruthenium correspond to an increase in activity, whereas little amounts of ruthenium correspond to a decrease in activity. But now, showing just the correlations does not necessarily imply causality. So if you would go on the internet and look up the site of Tyler Wiegand, you will find a whole database of spurious correlations, which are just parameters that happen to correlate. And over here I have an example. The distance between the Saturn and the Moon correlates with the number of bachelor degrees awarded in physical sciences. And since last year, Tyler updated his website to also include ChatGPT explanations to these correlations. So if you go there, you can also download a paper that is looking into this correlation. So please, if you want to have fun, look it up, but not during the talk. We are still busy. So how do we evaluate if the correlations we observed in our experiments are not spurious and are related to some physical phenomena? So for that, we went back to our theoreticians. So I asked Jack to come up with a theoretical model that can explain the CO oxidation reaction. So breaking down the CO oxidation reaction into elementary steps, we end up with these three major steps. In the first step, we have CO bound to the surface, and we need to bind an OH next to it. After that, the OH and CO combine into a COOH molecule, and then CO2 leaves the surface. So if you would now look on the descriptors for this reaction pathways, we have three types of binding energies we can look on. We can look on the OH binding energy, CO binding energy, and the COOH binding energy. And how do we know which of the descriptors is correct? For that, we can compare it again to our experimentally obtained data set and see which of these models best replicates the mathematical landscape that we have in our experiments. And now we see that the binding energy of OH has the best reproduction of our experimental data set. In addition, in these DFT calculations, Jack was also varying the fraction of the surface that was considered in the calculations. And it turns out that you get the best correlation also if you take only the top 5% of the active size into account. And that explains why our optimum is such a large domain. If you just need 5% of the active size to be active for the CO oxidation, you don't need to add more ruthenium at some point because it will not increase the activity. So I think the nice thing about this work is that it illustrates a very nice synergy between three fields, between mathematics, experiments, and theory. So mathematical algorithms can drive our laboratory experiments to provide more efficiently a data set. After that, this data set can be used to construct correlations, which using theory can produce an interpretation and a better understanding of our chemical processes. In turn, these interpretations will lead to new hypotheses, which will be tested using the scientific method, and a loop will close off and continue. So myself, I am an experimentalist, and my biggest interest is into looking how we can optimize the generation of the new data. And the question that automatically pops up is that once we have found a way to construct models for five-element systems, why should we limit our studies to 5-element systems and not go up? For this, I would like to discuss this question using this example. So let's say we have a model for this gold, iridium, osmium, palladium, platinum, rhenium, rhodium, ruthenium space. If we know the model for this space, we should inherit the model for the gold, iridium, osmium, palladium, platinum space. Likewise, for this space, that space, and in total there are 56 5-element spaces trapped in this 8-element space. So if we now take these 50 experiments as a guideline for the number of experiments we need to study an individual 5-element space, we end up at 2,800 experiments that we need to invest to study all possible combinations. So this has to do with the fact that if you go up in dimensions, the number of experiments is growing according to the combinatorics. So you calculate the number of spaces encapsulated. But the number of experiments that we need to study a combined space grows exponentially, and that results in this red curve. So if we want to study an 8-element space with the same information density as a 5-element space, we only need 940 experiments. So we save 1,900 experiments by studying everything together. So usually a couple equations would already prove that the concept works, but people would like to see how it works in practice. So I went on to do a very tedious screening where I synthesized 350 different nanoparticles. 200 particles were chosen in this 8-element space, and then 50 were taken in each of the selected 5-element spaces. After that, I used these nanoparticles to evaluate their electrocatalytic activity towards the oxygen reduction reaction. And here I was very happy to have a multi-working electrode that allowed me to perform 6 measurements at once. So to put things into perspective, it took me around half a year to obtain the entire data set. Without this multi-working electrode, I would need to spend 3 years. And that is, I would say, on the top of my PhD time. So that would have been not feasible. So now as I have a data set composed of different compositions and their associated activities, I can go on and train different models. And now we need to find a way to also evaluate the performance of these trained models. And for this, we use the so-called cross-validation methods. In the cross-validation method, you take your entire data set and you split it into a test set and a training set. This training set you then use to fit a Gaussian process, and then you predict the values for these test data points. And by taking the difference between the prediction and the true value, you can get an overview of how well the Gaussian process predicts unseen values. So the mean absolute errors that you see over here are a reflection of how well a Gaussian process predicts unseen values instead of how it fits seen values. So using these 200 experiments, we fit an 8-element model and we obtain an error of 0.114. We can now use this 8-element model to predict the 50 unseen experiments in each of the 3 selected spaces. And we get for the gold, osmium, palladium, platinum, ruthenium space a mean absolute error of 0.135. In case of the iridium, osmium, palladium, platinum, ruthenium, an error of 0.077. And in case of iridium, osmium, platinum, rhodium, ruthenium, an error of 0.075. And the errors by themselves are not meaning much, unless we have something to compare it to. And the best thing we can compare it to is to see how well we would have known these spaces if we were to study them using these 50 experiments. So in blue, we see the results of the leave one out cross-validation for the 50 experiments in these 5-element spaces. And now we see that the errors of these 5-element models are very similar to the prediction error of the 8-element space. So that means that the 8-element space learned a very similar model. So it has extrapolation strengths towards these edges. And now we can extend this conclusion. And as we know that the 8-element model has decent prediction in these 3 selected 5-element spaces, it also has predictive power in the unseen 53 5-element spaces. With this, we can construct this wonderful map that tells us what the most active composition is in each of the 56 5-element spaces. And we can order them and rank them by their performance. The most active catalysts are always found in a subset that contains platinum, palladium, and gold. Medium activity samples can be found where you have a combination of either platinum, palladium or platinum, gold. And then we have all the others. The other thing that I find very interesting about this map is that it illustrates how little actually is relevant for industrial applications. Among 56 5-element samples or 5-element spaces, only 10 are producing relevant results for further studies. Conveniently, it also turns out that the 3 investigated spaces each belong to a separate activity class. So we can take a look on how well the 8-element model can predict the activities. And now we see that there is a large discrepancy. In gold, osmium, palladium, platinum, ruthenium, the 8-element model predicts that osmium is part of the optimum, whereas the 5-element model tells that that is probably an artifact. Likewise, in the least active space, the iridium, osmium, platinum, rhodium, ruthenium, the 8-element model predicts a single optimum, whereas the 5-element model predicts that there are 2 optima. So the reason for this discrepancy can be attributed to the undersampling of the 8-element model. So remember, in the initial calculations, we needed to do 950 experiments. Due to time constraints, we limited it to 200 experiments, so we lack a bit the pinpoint accuracy. However, the good thing is that the hierarchy is still predicted correctly. So while the pinpoint accuracy is lacking, the hierarchy that we have is still correct. The gold, osmium, palladium, platinum, ruthenium is the most active subspace of them all. So the map that we have seen previously is still valid. So now we can move on and do the same thing as we have been doing in our previous works, and that is comparing DFT calculations to our experimental work. So now with DFT calculations, you have exactly the same problem about the exponential scaling of calculations. So doing a calculation for a 3-element space is expensive, for a 5-element space is very expensive, and for an 8-element space, it's basically impossible. It was impossible. Now with machine learning advances and using neural network, it became possible. So for this work, we decided to limit us to the most active subspace, which is the gold, palladium, platinum subspace. And the DFT calculations demonstrate that there is a local optimum on a similar location as the optimum predicted by the 5-element space. However, the DFT calculations also show that there is a global optimum in the platinum corner, which we are missing in our Gaussian process. So the Gaussian process also has an associated certainty to its predictions, and this is the one you can see in the circular overlay. So basically, in this corner, we have no certainty in our prediction, and this has to do with the fact that there are no experiments in the corners. So eventually, we started with 8 elements, we funneled it down to a 5-element space, funneling it down to a 3-element space, and it turns out that the most active catalyst for the oxygen reduction is still the pure platinum catalyst. And I would say this is not the first study that ended up in a disappointment, because if you look into literature, you will find other screening studies, and most of them end up also with the same conclusion that the most active catalyst is a binary, or in some cases, a ternary alloy. So can we explain why it's so hard to find a high entropy alloy? And for that, I would like to take another look on the theory behind high entropy alloy catalysis. So let's say we have, again, a pure metal surface. All sides are going to be identical. So if we are going to construct now an activity distribution diagram, we get a very boring figure. It is just a single point with 100% active sides with the same activity. But now as we start to alloy it, we add elements that are going to perturb these activities and increase the activities of these active sides. So we form an activity distribution which now looks like something like this. Our most active sides shift up in activity, but at the same time we have introduced ligands, and these ligands are not necessarily active towards the reaction, but they still occupy the surface. So we end up also with a fraction of inactive surface, which we can assume to be dead. So an alloy is only competitive with its counterparts if it can compensate also for the loss in surface. And in a random system, this distribution is governed purely by statistics. So we can construct a statistical model to evaluate these activities that alloys need to have in order for them to be competitive with their counterparts. So let's derive this statistical model together. The very first thing we need to do if we are making a model is to get our definition straight. So in this case, I decided to define an active site as this 7-atom arrangement, 1 center atom, 6 atoms in the surrounding. So if we now have a 5-element alloy, we end up with 78 possible different active sites. I don't think people like to work with such a large amount, so let's simplify it. And let's group active sites based on their complexity. And the way we now group them is we define the active sites are similar in activity by their center atom and the number of distinct atoms in the surrounding. So a binary alloy we can describe now using 4 types of active sites. We have the pure sites and we have the binary sites. Moving on to an example of a ternary alloy, we now have 9 types of active sites. We have the 3 pure sites, we have 3 types of binary sites and 3 types of ternary sites. And the same thing we can do for all other alloys. So now, as we have defined the active sites and grouped them together, we cannot assign an activity to them, but we can already group them how we would see them in our activity distribution. So the more complex an active site is, the more you invest to make it, the more active it should be. Because if it doesn't make up for its activity, it's not worth to go up in complexity. So the 5-element site is expected to be the most active. So now, having all these definitions, we can start to calculate our activity distributions. And here I decided to go with 2 additional assumptions. One is we are interested in compositions that will maximize these most active sites. So the compositions you can see over here will maximize the fraction of the most active and most complex site that there is. And also, to simplify everything else, we assume that only active sites containing metal 1 in the center are active, and the rest can be ignored and considered inactive. So we see the following thing happening. Going from a pure metal to a binary alloy, we end up with an electrocatalytic surface that only has 72% of the surface active. In case of a high entropy alloy, we only have 24% of our electrocatalytic surface. At the same time, the fraction of the most complex site is also decreasing. A bimetallic site has, in the best case scenario, 62% of the surface, whereas a 5-element site has, in the best case, only 4% of the surface. So now we can also calculate these minimum activities that these sites need to possess to outperform their counterparts. So here I would like to illustrate it on an example. If we start with a pure metal catalyst and we make a binary alloy, we lose 90% of the pure metallic surface to get 62% in return. So the only way this binary alloy is going to compete with its pure metallic counterpart if these binary alloys have an activity of 1.4. We can continue this calculation pairwise, and now we see the struggles that high entropy alloys face. For a 5-element alloy, for a 5-element site to outperform its counterparts, it needs to fulfill multiple rules. It needs to outperform its pure metal counterparts by 22 times, its binary counterparts by 40 times, and its ternary counterparts by 8 times. So these numbers without any context don't mean much. So let's grab the oxygen reduction reaction as a context again. The oxygen reduction reaction is limited by scaling relations. And the binding energy of the OH intermediate on platinum is 0.1 eV away from the top of the volcano. So the optimal activity of the ideal catalyst we can express in platinum equivalents, and that will be around 50 times the activity of platinum. So now we have an upper limit in how active our active sites can be. And thus we can calculate how much of an activity increase we can get from going up in dimensions and making alloys. A binary alloy can increase the activity relative to platinum by 30-fold if all the binary sites are going to be ideal. But in the case of a high entropy alloy, we can only double the activity, simply because we just have 4% of the surface area devoted to 5-element sites. We can also calculate which binary and ternary alloys high entropy alloys will not be able to outcompete, simply because of lack of surface. So if you find a binary alloy that doubles the activity of platinum, a high entropy alloy cannot outperform it anymore. And that probably explains why within our screening studies, all screenings end up in these binary and ternary catalysts. So this picture of high entropy alloy catalyst now allows us to also get a qualitative relationship between the entropy and the activity. So the entropy is a measure for the degree of alloy. So as we are making an alloy, we introduce ligands, and these result in an increase in activity. But at some point, we reach the optimal ratio between the site abundancy and its activity. And if we continue to increase our entropy, we start to dilute the number of these active sites. So we end up with a worse catalyst. And in case of the oxygen reduction reaction, this optimum can be found at around a binary catalyst. But now let's take a look at what happens in case of the oxygen evolution reaction. So in the same screening study I was doing for the oxygen reduction reaction, I also measured the oxygen evolution reaction. Because, well, doing an additional measurement for 15 minutes is maybe sometimes worth it. So here we end up with the same process. We have a model that now can correlate the different compositions to the different activities. and we can predict the different optimal compositions for multiple potentials for the oxygen evolution reaction. And here we see two things. The first thing is that the optimal composition is always a 5-element arrangement. The other thing that we can see is that the optimum composition is potential dependent. The more you go up in potential, the less ruthenium you have in your system and the more osmium you get in return. So the reason why we have a change in optimal composition has to do with the stability of ruthenium in acidic environments. Ruthenium is a very active catalyst for the oxygen evolution reaction, but incredibly unstable in acid. So ruthenium-rich samples, they tend to show these peaks due to the decay of the catalyst. Whereas if you have a moderate amount of ruthenium, you have this exponential increase. But still, we cannot explain why we see 5 elements. So we went back to our theoretician friends, and in this case, Dr. Katrien Zwaan did the calculations, and she modeled the iridium, osmium, palladium, platinum, rhodium, ruthenium space. So rhenium was excluded because we did not observe it ourselves to be incorporated into our alloys, and gold had to be excluded because it was popping out of the surface, giving an erroneous error in the calculations. And she observes that ruthenium and palladium have a synergetic effect. So the optimal catalytic sites are either a combination of ruthenium and palladium or pure iridium. But she cannot explain why we have gold and osmium incorporated into our system. So for this, to understand it, I would like to introduce you to two new concepts, and that's the difference between the intrinsic activity and the effective activity. So when we are doing calculations, we are looking at the intrinsic activity of the catalyst. And this is the activity of a catalyst under ideal conditions with a very well-defined surface. And this is also the same activity that has been analyzed using the statistical model. But the moment we take our catalyst and we put it in our electrocatalytic setup, we are going to measure the effective activity. So we are going to measure the result of possible surface reconstructions. We will be affected by the stability issues, by mass transport and internal resistances of the setup, and many more. And in this case, we believe that while the most active sites are a combination of ruthenium, palladium, and iridium, gold and osmium are necessary to stabilize the system and allow us to measure it in our electrocatalytic setup. So with this, I would like to move on towards the end of my talk. In this talk, I have covered multiple topics on high entropy alloy catalysts. I have demonstrated the use of Bayesian optimization to accelerate the search for novel high entropy alloy catalysts. And I also showed that by going up in dimensions, we can further accelerate the data acquisition. Also, based on our empirical insights, we can see that high entropy alloys are struggling to compete with the binary and ternary counterparts. So my advice to the field would be to start focusing on secondary properties of high entropy alloys that are going to be unique to them and unseen in binary alloys. This could be looking into aspects such as the self-supporting property of a catalyst. So your support becomes a part of the matrix of your catalyst. It can be seen, you can look into the morphology control. So you add elements that are going to leach out specifically, creating a specific morphology that is highly active. And of course, we can look into the stability on how stable is a high entropy alloy catalyst, because that's a completely unknown question. With this, I'm going to thank all the collaborators on the work that I have presented. And I would like to thank you as well for your attention. Yeah.
But just as a general sense, like how stable are these high entropy?
That's unknown. So from thermal perspective, high entropy alloys are considered very stable because as you increase the temperature, your entropy takes over. So you create this disordered structure. And the moment you quench it or cool it down, it gets kinetically stabilized because you have a disordered structure. So the atoms don't want to migrate. But when it comes to catalysis, you look at the surface. So there, these laws do not apply anymore because you can, how to say, segregate over the surface and you can hop over the surface. So it's a big question whether the surface is segregating or not in case of high entropy alloy material catalysts.
I'm just curious about high entropy alloy here.
Yeah.
So does it form any phase? Or is it just kind of mixture of different elements and you call that entropy alloy?
So based on the theory, it should create a single phase. But because we're making nanoparticles, we get typically a mixture of phases because they cannot, now it's called, statistically, you can get indeed also nanoparticles that have a different phase. So the presence of multiple phases is not excluding the presence of a high entropy alloy phase.
So these nanoparticles, they form kind of analogical bonds. Still kind of like a discrete particles.
They are separate particles. So you mean if they are agglomerating or not?
Yeah, or just because normally when we make alloy,
Yeah.
we melt them and we make it
Yes.
form an intermetal compound or
Yeah. Okay.
Solid.
So in this case, we use the wet chemical synthesis approach. So you take the precursors, which are the salts, and then you, anneal them at high temperature in a solvent. And because of that, they create what's called seeds at which grow different nanoparticles, so they are not connected to each other. And they just cluster together. Yes. Yes.
Like, does that have an effect on the activity and then later the prediction, like compared with the predictions?
So we did not look into the size effect. In general, the size has an influence if you look on the nanoscale size. So nanoparticles in this case are above 5 nanometers, so you don't really have the the size effects in terms of activity. So the activity should be more or less the same, but you get an error in the surface area. And that would account for a spread and mismatch in the prediction, of course. So that's experimental noise in this case, which we say work around with. Yes, it's an aspect that influences the final measured activity.
Yeah, like following up.
Yes.
So for each one of the compositions, when you're doing the Bayesian optimization with the experiments, how many experiments do you have to, experiments you have to do per composition, like different syntheses and so on, so you can get like a spread and have an error per composition?
I would say that's a good question. It's, I would say, up to you to decide how, let's say, reproducible you want to have your data. There is a aspect of Bayesian optimization that, as Bayesian optimization chooses a point based on a certainty, if you take into account your experimental error, then there's always a probability to improve the already known point by repeating it, because it is not a fixed value. So for Bayesian optimization to work, you need to assume that you have no error in the current process. And then it's, I would say, to you to decide how many you need for a statistically relevant data. Yes.
Someone has asked, I was wondering if there are any guiding principles for selecting the initial metal combination in the test data and in the optimization process.
Not yet. There are no yet guidelines on what to mix. Our rationale was based on the noble elements, because these are the most stable and the well-studied model systems for the classical energy conversion reactions. So that's why we would have a model that we can relate then to a very strong base of literature. That was our rationale.
But very nice talk, first of all, very insightful. So then when you mentioned at the beginning, you said that the metals have like a discrete binding energy for a certain reaction. The fact that now an alloy has sort of a band is not that means that it could be selective for one reaction pathway or another, like in the oxygen reduction peroxide or water. So I don't know if you could comment on this.
I can comment on it, and unfortunately this is not my work, so it's a work from Alexander Beggar, and he looked into the selectivity for the CO2 reduction on copper-based alloys. And here we, as I understand it now, if I look on these results, we see again that the statistics play a role. So because you now introduce a variety of different active sites, you lose control over your selectivity. So you lose in a way also control on the amount of different active sites you have. So while you get an active site that is very good for one pathway, you also create other pathways.
If I may as well. So when I didn't quite understand when you were talking about the ligand effect, and you were saying that in an alloy, so that if you have a pure metal, you have all of those active sites, but then when you have an alloy, then you mentioned that you lose active sites, but essentially it's the way I see it is that you still have everything is active, is an active site. How do you think? Because it feel like you were talking about platinum being the active side and all the other metals being the environment.
Yes.
But the way I see it is just I mean, so you're not taking into consideration all the other metals are active, but
So I consider them inactive relative to that, because they have a much different binding energy, but it doesn't necessarily fall into the top. They then have an activity that is 98% of the most active sites. You can consider them as inactive. That is where it comes from. And if we look on the binding energies over here, so this is one I got from real data, real DFT data. So we have some active sites around the top, but we also have these sites, active sites, and the color now represents the metals for which these binding energies are calculated. And these can be considered inactive because they are so far away.
So then you think that
model, I do have a correction, assuming that the second element also participating in the reaction, but I skipped it in this presentation to make it simpler.
so essentially you think that for designing high entropy alloys for a given reaction, you should always include the state-of-the-art catalyst. Say for oxygen reduction, you should always include platinum. For CO2, maybe gold.
Not necessarily. So if you get a platinum-free catalyst, you could potentially find a high entropy alloy that has to the same activity as platinum, because that's not contradicting the constraints that we have. But they will not be able to rival a binary platinum catalyst in terms of activity. If the target is to have the most active catalyst, you need to stick to platinum-based catalyst. If you want to have something cheaper on the market, well, maybe there is a chance. And the only way to know it is to study it.
Yeah. All right. Thank you so much.
One of the main properties for the high entropy alloys is it has very low diffusivity, so low diffusion coefficient.
Yes.
Does it affect on the activity of the for the catalytics?
Diffusion of the within the solid.
I mean on the surface as well, because it causes more lattice distortion here.
I'm not sure if the surface is affected by the sluggish diffusion, because now you can, how to say, you are uncoordinated. So the surface elements are generally more common.
But I thought it's because we have more different elements cause lattice distortion.
Yes.
So, so certainly it depends on active site, but also because of the stress field on the free surface here. That
inside. So as
also on free surface as well. Yeah, certainly that's trying to kind of equilibrium stress state, and you have more lattice distortion because you have different atomic size.
Yeah,
that's a lattice distortion not only inside solid but also on free surface as well.
Right. And that should increase or decrease the energy necessary for an atom to eject into bacon.
Yeah,
that's something to still study. Yeah. But when it comes to catalysis, in general, that doesn't matter, because if you bind a catalytic intermediate on one side, for it to diffuse to another side, you need to invest in energy. So that would also go into your reaction energy, have this migration over the surface. So, and that would account for the same energy as to just straight absorption. So whether your reactants can diffuse freely over the surface or not will not really change the catalysis.
Thanks.
Rain or?
Oh, go ahead.
No, go for it.
So I had a question about the three secondary properties that you mentioned on your conclusion slide. Would the idea be to like experimentally define an initial like training data set and feed that into your machine to predict the properties of like different combinations?
Yes, but for that you need to generate your data set. That is the challenge basically. to get reliable, large enough data set to make such predictions. So right now, my former supervisor and Jan, together with Alfred Ludwig and Karl Meyerhofer, they have a ERC grant to study these morphological changes in high entropy alloys. So that's upcoming work.
For your system where you have 6 electrodes on the RDE, how do you know that there's not yet some dissolution occurring that is then changing the properties of the catalyst from one electrode to another?
You mean crosstalking in this case? Because they are, so what I did is taking the same catalyst in all of the 6 electrodes. It's the same material everywhere, and it doesn't then matter whether it would be 1 electrode or 6 in parallel. They're not cross-contaminating each other.
You're just doing 6 repeats.
6 repeats at the same time.
Does it make it faster then, or?
Yes.
Go ahead.
Because you get 6 independent statistical, say, curves for each of them instead of 1 big statistical aggregate. If you then have to take into account loading, or so we normalize in this case by the capacitance, you get also a better way to check the reproducibility of the electrocatalytic performance. Questions?